Hey everyone, and welcome back to the channel. Today, we're diving deep into a topic that's revolutionized modern infrastructure management, infrastructure as code, or IAC. Specifically, we're going to explore how to create a highly scalable and robust AWS architecture using Terraform, a powerful and widely adopted IAC tool. Have you ever wished you could describe your entire cloud environment in plain code, version it, and deploy it with a single command? Well, that's exactly what we're going to demonstrate today. We'll walk you through building a foundational AWS setup, complete with a virtual private cloud, secure subnets, an EC2 web server, and a private RDS database, all defined and deployed declaratively with Terraform. This isn't just theory. We'll discuss the practical aspects, including how to structure your Terraform code using variables and outputs, and even how to integrate it seamlessly into a CI/CD pipeline. Whether you're a seasoned DevOps engineer or an IT student just starting your cloud journey, this video will provide you with a comprehensive understanding of deploying scalable infrastructure on AWS using IAC principles. So, buckle up, because we're about to transform how you think about cloud provisioning. Let's get started. First, let's understand why infrastructure as code, and why Terraform specifically, has become indispensable in the cloud era. Imagine provisioning dozens, or even hundreds, of cloud resources manually through the AWS console. It's tedious, error-prone, and nearly impossible to replicate consistently. IAC solves this by treating your infrastructure like software. You define your desired state, what resources you want, how they're configured, and how they relate, in human-readable code. Terraform takes this code and translates it into API calls to your cloud provider, in our case, AWS. The benefits are immense: consistency, speed, version control, auditability, and reduced human error. You can easily roll back changes, test new configurations in isolated environments, and ensure that every deployment is identical. Terraform, being cloud agnostic, allows you to manage resources across various providers, but its deep integration and powerful state management make it a top choice for AWS. It's declarative, meaning you describe the what, and Terraform figures out the how. This fundamentally changes the game from manual operations to automated, reliable deployments. Now, let's talk about the specific architecture we're building today. Think of it as the backbone for a typical web application. At its core is an AWS Virtual Private Cloud, or VPC. This is your own isolated, private network in the AWS cloud, where you launch all your resources. Inside our VPC, we'll create both public and private subnets across multiple availability zones for high availability. Public subnets are for resources that need direct internet access, like our EC2 web server. Private subnets, on the other hand, are for sensitive resources like our RDS database and application servers, keeping them insulated from direct public exposure. To enable internet connectivity for our public subnet, we'll provision an internet gateway. For instances in private subnets to initiate outbound connections, e.g., to download updates or connect to external APIs, while remaining private, we'll deploy a NAT gateway. This structured network foundation ensures both connectivity and security, laying the groundwork for a robust, scalable application environment. It's like designing the perfect roadmap and security checkpoints for your digital city. Let's dive into the core of our Terraform project, the main.tf file. This is where we declare our AWS resources using HashiCorp Configuration Language, or HCL. We start by defining our AWS provider and the region where our infrastructure will live. First up is the VPC itself, our main isolated network space. We'll specify its CIDR block, which defines the IP address range. Think of it as drawing the outer boundary of your private cloud data center. Next, we define the Internet Gateway, which acts as the bridge between our VPC and the vast Internet. Without it, public traffic can't flow in or out. Then, we declare our public subnets. These are the subdivisions of our VPC, strategically placed in different availability zones for fault tolerance. We configure them to automatically assign public IP addresses to instances launched within them. Each resource block in main.tf corresponds to a real AWS resource that Terraform will create, update, or destroy, adhering to our declarative configuration. It's a precise description of the infrastructure we want, resource by resource. Building upon our basic network, let's connect the pieces. After creating public subnets, we'll define our private subnets, again across multiple availability zones. These are crucial for hosting back-end resources that shouldn't be directly exposed to the internet, like our database. For instances within these private subnets to access the internet for updates or external APIs, but without being directly reachable from the internet, we need a NAT gateway. We'll provision an elastic IP address for the NAT gateway and place the NAT gateway itself in one of our public subnets. This setup allows private instances to initiate outbound connections securely. Routing is handled by route tables. A public route table directs traffic from public subnets to the Internet gateway, while a private route table directs traffic from private subnets through the NAT gateway. This careful orchestration of subnets, gateways, and route tables ensures that traffic flows exactly as intended, providing both connectivity and a strong security posture for different layers of our application. With our network foundations in place, let's bring in our compute layer, the EC2 instance. This virtual server will act as our simple web server, residing in one of our public subnets, meaning it's directly accessible from the internet. In our main.tf, we define an AWS_instance resource, specifying its AMI, Amazon Machine Image, which is essentially a template for the operating system and initial software. We'll also pick an instance type, like t2.micro for a cost-effective test. Crucially, we attach a security group to this EC2 instance. Security groups are virtual firewalls that control inbound and outbound traffic. For our web server, we'll configure it to allow SSH, port 22, for remote access and HTTP, port 80, for web traffic from anywhere. We also include user_data, a script that runs when the instance first launches, to automatically install and start an Apache web server and serve a basic Hello World HTML page. This demonstrates how Terraform can not only provision infrastructure but also perform initial configuration, making your instances ready to serve immediately. Now, for the data persistence layer, the RDS database. Security is paramount here, so our RDS instance will be deployed into our private subnets, ensuring it's not directly exposed to the internet. We define an AWS_DB_instance resource, specifying the database engine, like PostgreSQL, its version, and the instance class. A dedicated DB subnet group is created, which spans our private subnets, allowing RDS to distribute database instances across multiple availability zones for high availability and disaster recovery. Similar to EC2, the RDS instance will have its own security group. However, this RDS security group is carefully configured to only allow inbound connections from our EC2 web server security group, specifically on the database's default port, e.g., 5432 for PostgreSQL. This creates a secure, internal communication channel between your web server and your database, preventing unauthorized direct access. Terraform ensures all these intricate connections and rules are correctly established, maintaining the integrity and security of your data. To make our Terraform configuration flexible and reusable, we leverage variables.tf and outputs.tf. The variables.tf file allows us to define input variables for our deployment. Think of these as customizable parameters. Instead of hard-coding values like the AWS region, project name, or even sensitive database credentials, we define them as variables. This means you can easily deploy the same